And welcome back to Blyle's wacky chemical principles, the craziness, the silliness, the comedy routines. Hi, Kim.
I
Always nice to have Kim here. Um, nice to actually be talking with somebody as opposed to talking to a lifeless, cold, bitter, um, unanimated ex-wife, computer. Uh, that's a joke. She is nowhere near a computer. Anyway, we've been talking about classical thermodynamics, not quantum, but thermodynamics. We started off with the zeroth law, which defines heat. First law, which defines energy, although in chemistry we use enthalpy, which is sort of a watered down version of energy and leaves some terms out. So we use enthalpy. We talked about entropy, and we decided that entropy can be thought of as disorder, but is better thought of as sort of knowledge. The higher the entropy, the less knowledge we have of a system. Because it's related to the number of available quantum states, W, which gives us a very nice little equation. K log W is entropy. It's just that simple. We also talked about spontaneity, which is where we kind of left off. Spontaneity. Now, enthalpy tells us if a reaction is exothermic or endothermic. Where's my... Oh, I'm having some technical difficulties here. Hang on one sec. I'm having some technical difficulties. I apologize for that. We are here. It is. That's the reason. Yes, it should be active again. Why are you no longer active? Be active. We're gonna do that. And then we're gonna do that. We're gonna do that. And we're gonna do that. Now it should be active. Now where's my, there it is. There it is. All right. Okay. So enthalpy tells us if the reaction is exothermic or endothermic. Remember, delta H negative means exothermic, which is usually favorable. Delta H positive is endothermic. The second law taught us about entropy. Delta S positive is usually favored. That means entropy is going up. But sometimes delta S is negative. Water is probably the easiest example of this. When water evaporates, that's why we sweat, it absorbs heat. So we sweat, the water evaporates, delta H is positive. We say that's an entropy-driven process. It's not driven by enthalpy because enthalpy is positive rather than negative. So it has to be entropy that's making it happen. When water freezes, or when it recondenses into rain, it's very day to day. It's threatening rain, which means that the water, which started off as vapor, is condensing into droplets. It is going from a higher entropy gas state to a lower entropy liquid state. That must be enthalpy driven. Entropy always wants to increase. So In water processes, evaporation, condensation, all that kind of stuff, you have two opposing forces, and they're going sort of opposite each other. Enthalpy is trying to get this to the more condensed states. Entropy is driving it towards the less condensed states. And which one wins out? That is why we use free energy. In the case of chemistry, we are using specifically Gibbs free energy. Free energy is the energy available to do work. So if it turns out negative, if the free energy turns out positive, that's how much energy has to be put into the system for it to occur. Non-spontaneous reactions do occur, but they're always coupled. They always occur with some other source of energy input. Your body does this all the time. That's what ATP does. In a lot of your chemical reactions and a lot of the processes, your body, you're a walking, talking chemical reaction. The sum total of the chemical reactions that keep you alive is called our metabolism. It's metabolism, catabolism. But that's what keeps us alive. Some of those processes are not spontaneous. That means that in order for them to occur, and they must occur, we'll talk about this here before the end of the semester. For those reactions to occur, there has to be an external source of energy. Often, I would even hazard to guess, usually, that external source of energy is ATP, which is a temporary energy storage. It's very unstable, so it doesn't stay ATP very long. It's not like form ATP up here in a shoulder cell, and the next thing you know, it's being used in your knee. It's used internally within one cell. It doesn't travel much, but it temporarily stores energy. And that's the energy that makes non-spontaneous reactions occur. It's coupled. If we went into biochemistry, we would talk about some examples of that. Excuse me, sorry about that. But Gibbs free energy, we gave a very nice little equation here. Delta G is equal to delta H minus T delta S. So there's a change, delta free energy, the change in free energy is equal to the change in enthalpy minus temperature times the change in entropy. And what's always fascinated me about this equation, it doesn't change entropy, but it changes, the temperature changes the influence of the entropy term, just the influence of the entropy term. At absolute zero, that goes to zero. And whether or not it's spontaneous depends solely on the enthalpy. Of course, if it's giving off heat, you're not at absolute zero anymore. But, oh, sorry about that. Noosh, sorry, I didn't get much sleep last night. So entropy is the variable here. It's the contribution of entropy that can be made higher at higher temperatures or lower at lower temperatures. The importance of entropy is very temperature dependent. So let's do a quick calculation. I could not find a textbook in time for class today. It's very sad. So I found this data on a website. It was a website that looked quite respectable. It was a university website, so I believe it's correct. And let's do a quick calculation. Last time, the example that I used and states are very important in these calculations. You must know the states because this data includes states. So water, for example, is present in these tables as liquid, solid, and gas. So you have to look up the correct one. Now we know this is going to be spontaneous. We have seen methane is burned frequently. So we know it's going to be spontaneous. So why are we doing it? Because it's a good example. And when we start talking about kinetics, I'm going to continue with this example. So how do you do these calculations? Well, you look up the enthalpy. You look up the table. The table will give you the enthalpy of formation. It will give you the entropy, and it will give you Gibbs free energy. Normally, I will not even write down Gibbs free energy. You write down the enthalpy, you write down the entropy, skip the Gibbs free energy. Because remember, entropy is not temperature dependent, enthalpy is not temperature dependent, but Gibbs free energy, well, here it is. Gibbs free energy most certainly is temperature dependent. That table is usually at 298.15 Kelvin. It's what they call room temperature, but room temperature is really, really hot. 298 is 20 degrees Celsius. That's a very warm room. That's like 80 degrees. That's high 70s. I want to know, you see, the problem is I want to use this as heating fuel. So I want to know if this reaction is spontaneous at, let's say, 15 degrees Celsius below zero. Is it still spontaneous at a very, very, very cold temperature? So I look up in my table these species, and I find that methane, I find these numbers. Sign is very important. I'm writing down the Gibbs free energy, but I'm going to cross it out. But I'm writing it down because it is available in the table. Now, I told you anything in its elemental state is always going to be zero for enthalpy, but it is not zero for entropy. And hopefully there are no transcription errors. We are going to find out. Carbon dioxide. Kim, is this going to be spontaneous? Well, we already know it's going to be spontaneous. Do you think it's going to be exothermic or endothermic? What's your guess? Here's a big hint. It burns. When this reacts, you get flames. Is that going to be exothermic or endothermic? Kim doesn't want to play today, and that's okay. I pick on her too much. Of course, it's going to be exothermic. We're talking about flamage. Okay, this is our data. There are several things that we must understand about this. This little zero here tells us that this is at standard conditions. This is at room temperature. If we were running this at 20 degrees Celsius, we could just use this data, but normally we're not. So don't use this data. This is not, we're at -15. We're not at 298. We're not at 298 Kelvin. We're at 15, so we can't use this. Don't even bother writing it down. It's just not worth it. The second thing we have to note, always, always, always check your units. This entropy seems excessively high to me. And that's because our enthalpy is in kilojoules. A joule is a unit of energy. A joule is a unit of energy. It's like a calorie. But if I'm remembering correctly, and I might have it backwards, it's 4.184 joules per calorie. But it's like a calorie. It's a unit of energy. So enthalpy is in kilojoules per mole. Entropy in the table, and they always do this, I don't know why, is in joules per mole Kelvin. So you have kilojoules for enthalpy and joules for entropy. When you add these together, they must be consistent. You cannot add joules to kilojoules. So we need to convert these numbers. So before I do any calculations, the first thing I like to do is convert joules to kilojoules. There are 1,000 joules in a kilojoule, which means that entropy in kilojoules will be 0.186264. All I'm going to do is move the decimal point 3 places to the left. So I don't even need a calculator to do this. Just move that decimal point. I always put a 0 here. The 0 is not a significant number, but it is important. That 0 just makes it easier to see the decimal point. It's a reminder that the decimal point is right there before the first non-zero number. Now we're at kilojoules per mole Kelvin. And while we're at it, let's convert our temperature. To get to Kelvin, you add 273 to your temperature. Our temperature happens to be negative, so we actually have to subtract. We have 268 Kelvin. So we're not at 278. No, we're not at 298. 298. We're not at 298 Kelvin. We're at 268 Kelvin. So now we have our temperature, we have our entropy. Let's do our first calculation. First, to calculate the change in enthalpy. Remember, it is always, always, always product minus reactant, and do not forget the stoichiometric coefficients. So it's product, which means we start with carbon dioxide. And all we're really doing here, we have two waters. We're just adding these numbers up. So we do have to note the sign because those negative signs are going to make a difference. So it's products minus reactants. Now, I want to put the oxygen down. We really don't need the oxygen because the enthalpy of formation for oxygen is 0. Without our handy dandy calculator, no, I did that wrong. Notice that this negative sign is going to cancel this negative sign. And we get a negative enthalpy. Negative enthalpy indeed tells us that this is exothermic. We can actually use this number in calculations. We know that heat is given off because it's negative. How much heat is given off? Well, if we want to convert this to, let's say, the moles of oxygen, remember, you always have to use the stoichiometric coefficients. But you can figure out per mole of methane, per mole of oxygen. You can figure out how much heat is given off per mole of carbon dioxide or per mole of water. And you set it up just like a stoichiometric calculation. You can also figure out according to kilograms or whatever unit you want for any of these. So you can actually use this in a calculation to find out precisely how much heat is given off. For entropy, since we have kilojoules here, we're going to use kilojoules here. We made the conversion, we may as well use it. Some students, if you would prefer, can go ahead and measure, you can go ahead and use joules and then convert to kilojoules later. But I prefer just to use kilojoules. I'd rather do it in advance because, like I say, all you're doing is slipping the decimal point. By doing it in advance, I don't have to worry about forgetting to do that later on. It's already done for me. Now, if I were to predict if this is going to be an increase or decrease of entropy, I would not know what to tell you. We have the same number of moles on both the reactant and the product side. We have 3 moles on both the reactant and the product side. And we have all gases. Normally, entropy increases if you increase the number of moles. And it increases as you go from more condensed states, liquids or solids, to the less condensed states, like gas. In this case, they're all gases. It's the same number of moles. I don't know if entropy is going to increase or decrease for this reaction, but fortunately, I don't have to guess. I can do the calculation. Once again, products minus reactants. So we start with carbon dioxide. And water. Minus the reactants. Notice these are all positive numbers. Oops. Oxygen, sorry. There should be a Jeopardy theme song going right now, don't you think? If I did my calculations correctly, that is close. The entropy actually goes down. Entropy does not favor this reaction. It is almost zero. It doesn't go down much, but it does go down. By the way, notice that in entropy, we have this extra little unit in the denominator, Kelvin. That's because we're going to have multiplied by the temperature here. And because we must be consistent in our units, we have converted our temperature to Kelvin. So that unit Kelvin will cancel out. And yes, these calculations can be a little tedious, but we're getting a lot of information out of it. Notice it's very consistent. It's always products minus reactants. Always include the stoichiometric coefficient. And it tells us that this reaction is indeed exothermic, but the entropy decreases, which means this is an enthalpy-driven reaction. Entropy is trying to resist this reaction, but it is an enthalpy-driven reaction. But is it spontaneous? Remember, it is spontaneous if delta G is negative. And this is a case where it could turn out, if we get the correct temperature here, if we get the correct temperature, this will be non-spontaneous. Because we can force this to be positive. We just have to figure out the temperature where it will be positive. So now we can go ahead and substitute in our numbers. We have negative 802.335. Our temperature, we decided, is 268 Kelvin. With an entropy of negative 0.00515. Notice that the kelvins cancel. Notice that this negative sign cancels this negative sign. So we're going to add (1.3802). So the tax to make this reaction occur means we have to take 1.3802 kilojoules per mole out of the energy that we're getting from the enthalpy. And we end up with negative 800.95, rounding up to proper sig figs, 955 kilojoules per mole. It is negative, so it is indeed spontaneous, as we expected it to be. It is spontaneous. Now, I've said before, this is the amount of work you can get out of this reaction. So if I wanted to use it, if I wanted a methanol-driven car, methane-driven car, they're starting to capture methane in, like, from cows, cow flatulence. They're experimenting with capturing it as a fuel source. So if I put this into an engine, how much work could I get out of it? Force times distance work, 800, almost 801 kilojoules per mole of methane. And at STP, 1 mole is 22.4 liters. So you can figure out, force times distance, what is the mass of your vehicle? What distance could you drive? Well, until you're out of energy. And that's a maximum. That's ideal. That's assuming absolutely no loss in work at all due to friction or wind resistance or anything. That is the maximum amount of work we could get out of this. Let's do one other real quick calculation before we break, because I'm curious. At what temperature does methane not burn? It's an interesting question. So what is the temperature where this is no longer spontaneous? Well, if it is non-spontaneous, that borderline between spontaneous and non-spontaneous is when delta G transitions from positive to negative. And that transition occurs when delta G equals 0. So what temperature is delta G equal to 0? And we already know T delta S, so we can go ahead and just add that. Nope. Nope, we don't want to do that, because we know that's not 0. We're looking for the temperature. So in this equation, temperature becomes the unknown. We have to leave that in there. Move the temperature, move the enthalpy over, it becomes positive. Actually, let's do it this way. We're going to cancel out these two negatives. So we're at positive 0.00515 T. Move the enthalpy over, it becomes positive 802.335. By the way, I am skipping a lot of steps here because I assume you know what I'm doing. If I assume you know what you're doing, and this is something that is so important, if I make a basic assumption about your knowledge and that assumption is wrong, we've talked about this before. Who's at fault? Is it my fault that you don't know something? No. Is it your fault that you don't know something? No. There is no fault. If I'm assuming that you know these algebraic steps and you don't, that's just a weakness in your background. That is not your fault. It's just a weakness in your background. And what should you do about it? Let me know. I'd be more than happy to walk you through these steps, these algebraic steps, step by step, very carefully so you understand every single step. Once you get good enough at algebra, like me, you can kind of start to skip these steps. So in order to finish this, we need to divide both sides by 0.00515. One, two, three. So this reaction becomes non-spontaneous at an excessively high temperature, 155,000, actually close to 156,000 Kelvin. That's a huge number. I'm not even sure you would still have atoms or molecules at that point. At that point, they may just break down into a plasma. Holy cow. The temperature of the sun is 5,778 Kelvin. This is 150,000 Kelvin hotter than the sun. So no, at a practical temperature, this reaction will never be non-spontaneous. But technically, it could be. Technically. It's just not a practical temperature. But it is interesting to see that, yeah, if you go well beyond the plasma state, this reaction won't occur. Wow. We're going to take a quick break. We're going to talk about kinetics when we come back. Let's take 5 Kim. Let's be back here at 10:45, please. Oh, I'm so sorry. I'm a minute late. Wow. Okay. I'm very, very, very concerned about a friend of mine. So I just texted her, and I'm trying to be a good supportive friend. Methane is very spontaneous in its reaction with oxygen. It occurs naturally. And yet, you can go and buy a tank of methane. So why is it that the methane doesn't just explode automatically in air? And we've talked about this before. In order for this reaction to begin, we have to start by breaking those chemical bonds that are starting to get the reaction started. Once the reaction is started, it gives off enough energy to maintain and continue reacting, but we have to get it a little bit of energy to start. And if you recall, we suggested that this energy is called the activation energy. It's a spark. It's some sort of initial tiny little input of energy, and we get that energy back out plus so much more in a spontaneous reaction. But what really happens when a reaction occurs? What really has to happen? It's a mystery. It's a mystery that ranks right up there with why I'm still single. Why am I single? Did you ever stop to wonder about that? I'm a nice guy. Someone gave me some advice just a couple days ago, and it's always well-intentioned, and I always appreciate the intention behind it. Usually that advice is kind of what I call Peter Pan. All you have to do, if you want to meet someone, all you have to do is get out there and don't tell your jokes, because your jokes are terrible. And dress differently because I don't like the way you dress. And just avoid the topic of science. Don't talk about science, and just change everything that you are, and you'll meet someone like that. Oh, gee, thanks. Why am I single? Did you ever stop to think? Now, usually, most people will say, well, you just haven't met the right person yet. Did you ever think that maybe I have? Maybe I have met the right person. Did you ever stop to think about that? But maybe I didn't see her. Maybe she was in the grocery store and she was looking at pasta while I was looking at boxed dinners. And so we passed each other without even knowing. Is that possible? Is it possible we were in the same place and we just never saw each other? We just didn't turn around in time? Is that possible, Kim? Yeah, that's possible. We just didn't see each other. Our paths didn't connect. We were there, but they just didn't connect. Or maybe we did see each other. But maybe the day that we saw her, I just lost another job. And I'm wondering what I'm going to do next. And I'm not looking forward to having another job search. And she just got a ticket. And she has to pay that ticket. And her insurance rates are going to go up. So maybe we did meet. But what's the problem now? Aren't we at the wrong energy level? If our energy level is wrong, or maybe we're just both depressed because we're both single. We've been single for so long that it's just never going to happen. Why put in any effort? Chemical reactions are the same way. You didn't know I was teaching, did you? Chemical reactions are exactly the same way. What has to happen for a chemical reaction to actually occur? For a chemical reaction to occur, the reactants must meet. Hi, I'm Sarah. Hi, I'm Richard. Marry me. They have to meet. They have to actually come together. In a reaction with methane and oxygen, yes, you have methane and you have oxygen, but it's not going to react unless the oxygen actually comes in contact with the methane. But not only do they have to meet, they must be in the correct orientation. In other words, and I don't know, but suppose the methane comes in contact with the oxygen on the end. Here. That may not be what you need to actually start the reaction. Maybe what has to happen is it has to hit more or less in the center between the two bonds, the two oxygens. So if it's meeting, it also has to meet in the correct orientation or the reaction will not occur. It's not enough that they're both in the same aisle. They have to be looking at each other in the right way. And they must have the correct energy. For that reaction to occur, they have to meet in the correct orientation. If they have too much energy, they're not going to have time to react. They have to get close enough, long enough together for the old bonds to begin stretching and begin breaking. Because before new bonds can form, those old bonds have to break. And if they meet with too much energy, they just bounce right off of each other. They don't react. If they don't collide with enough energy, if the collision is too slow, those old bonds aren't going to start to break and they're just going to bounce off of each other. So for a reaction to occur, the reactants must come together in the correct orientation and with the correct energy. What we're talking about here is a reaction mechanism. So we're not going to go a lot into these. But a reaction mechanism is a proposal of the individual elementary steps for a reaction to occur, and they will add up to the overall reaction. So we have to propose, in our methane example, we have to propose that the methane and the oxygen will collide. In order for the reaction to activate. We never, no reaction mechanism has has three species coming together at the same time because it just doesn't happen. You can't do it. In two dimensions, we can have three things come together at once. But the odds of three reactants coming together at the same time for a reaction to occur, it can't happen. Maybe I'll give you an example of a reaction mechanism. Yeah, let's give you an example of a reaction mechanism. Not this one, because I don't know this reaction mechanism. So here's an example of reaction mechanism. Carbon monoxide is a bad gas. It's a silent but deadly, but in this case, it's real. Carbon monoxide is given off in any combustion reaction. Combustion reactions always produce some given amount of carbon monoxide. It's a side reaction, so it may not be much, but you're going to get some. It's odorless. I had a student who had a crack in her exhaust manifold, and she never understood why when she drove to school. She was always so tired when she got to school and always had a headache. These are the symptoms of carbon monoxide poisoning. Carbon monoxide reacts and attaches to the iron in your hemoglobin, deactivating your red blood cells, which means your red blood cells can no longer carry oxygen to the cells or carbon dioxide away from the cells. The only way your body can get rid of that is for that cell with the carbon monoxide attached to die and be replaced. Fortunately, that happens quite frequently. So it doesn't take long to recover from carbon monoxide poisoning, but there's nothing you can do. So if you have, even if you don't have, I'm going to recommend this, get carbon monoxide detectors. Carbon monoxide is a light gas, so put the detectors high. Put them high near your bedrooms. Put them high anywhere that you have combustion, even the garage. I have it in my kitchen because I have a gas stove. I have it in the stairwell above my basement because I have a gas water heater. I have a gas furnace. I have carbon monoxide detectors. Get carbon monoxide detectors, just like smoke detectors. They are so important. So what has to happen for carbon monoxide to react to form carbon dioxide? So here's a proposal. Here's a proposed mechanism. I'm going to assume that the carbon monoxide, don't try to figure out this Lewis dot structure because it is unusual. It does not follow the normal rules of carbon monoxide. Lewis dot structures. I'm going to assume that the carbon must collide with the oxygen lengthwise to form this really strange, funky little intermediate. Like this. This is called an intermediate. CO3. The double bond is beginning to stretch here. It's getting ready to break. And you form this funny little species. So in the first step of the mechanism, a carbon monoxide comes along and reacts with oxygen to form CO3, not a real compound, an intermediate. It's an intermediate. Intermediates are species that are not real compounds. They are not stable. They are somewhere between reactants and products. So don't think of this as an actual chemical. This is an intermediate. In a reaction mechanism, the intermediates must always fall apart. They must always cancel out. So I'm going to suggest that in the second reaction, in this intermediate, another carbon monoxide is going to come along here and take one of these oxygens away. So we start now with our intermediate. One of these oxygens is going to go with the new carbon dioxide. The other one is going to go with the old monoxide. The other one is going to go to the old carbon monoxide. Forming two carbon dioxides. Now notice two things about these intermediates. First of all, they have species that you don't normally see. They have these intermediates. Notice they are still stoichiometrically balanced. You still have 3 oxygens on the reactant side. You have 3 oxygens on the product side. 1 carbon here, 1 carbon here. In the second step, you have 2 carbons, you have 2 carbons. You have 4 oxygens, you have 4 oxygens. So they are still balanced. But now we can add them up. Anything in one step that shows up on the product side and shows up on the reactant side on the other side, they can cancel. And when you add up these individual reactions, they must add up to the overall reaction. So we have a carbon monoxide here and a carbon monoxide here to give us 2 carbon monoxides. We have 1 oxygen. We have 2 carbon dioxides. Everything in the first step cancels out. And that is our overall reaction. So this is a valid proposal. This is a valid proposal for a reaction mechanism converting carbon monoxide into carbon dioxide. There are things you can do. It's well beyond, this is actually well beyond the scope of this course, but just want you to understand what an elementary step is in a chemical reaction mechanism. And I want you to understand they have to add up to the overall. Does this occur? Well, honestly, anything that you can propose will occur in nature. We're talking about vast numbers of atoms and molecules and whatnot. So yeah, but it doesn't occur fast enough. That's why you need detectors to get out of the house. That is also why you have a catalytic converter on your car. I put a catalytic converter on my Chevy, but it's still a Chevy. You remember what a catalyst is? By definition, we talked about these earlier. A catalyst speeds up a chemical reaction, but is not consumed in the chemical reaction. So however much catalyst you add at the beginning, that is exactly how much catalyst you will get in the end. It is not consumed. That doesn't mean it doesn't participate. It has to participate or it does nothing. We write the catalyst usually above the arrow in a chemical reaction. That means that it participates, but it is not consumed. That is a catalyst. In your catalytic converter, you have platinum that is basically coating copper. So you have copper with a very thin layer of platinum. And here's how it works. you have these platinum atoms on the catalyst, and carbon monoxide will come along and attach itself to that platinum. Now I'm going to write this out this way at first. And then oxygen will attach itself to the platinum as well. So you have oxygen and carbon monoxide next to each other. One of these oxygens will go to the carbon monoxide, to form carbon dioxide. Leaving this oxygen on the platinum like this. When you were a kid, or if you have kids, what do you tell your kids if they get lost in a store, in a mall, something like that? You tell them to sit in one place, because the chances of finding that child is much higher if one of you is stable. So you tell the kid, just stand where you are. Don't move. I will be looking for you. That's kind of how platinum works. It holds that carbon monoxide until an oxygen comes along and it forms carbon dioxide. Well, that carbon dioxide is going to let go of the platinum. And another carbon monoxide is going to come along and attach here. You still have this oxygen. The carbon dioxide is gone, but now we have a new carbon monoxide. This oxygen is going to go with this carbon monoxide to form another platinum. No, the carbon dioxide, sorry. And then, of course, the carbon dioxide is going to fly off, regenerating the platinum. So we end up with the exact same catalyst that we started with. The platinum is still platinum. How would you write this down in a chemistry, in a reaction mechanism? Well, you would start with carbon monoxide. To form a platinum carbon monoxide complex. That platinum carbon monoxide complex, and actually this is going to be a slightly different mechanism because I don't know exactly how it works, but an oxygen is going to come along and see that carbon sticking out, and we're going to form a platinum carbon trioxide, which is kind of what this species is. So you have your platinum carbon monoxide and another oxygen comes along to form platinum carbon trioxide. Another carbon monoxide comes along, sees the platinum carbon trioxide to form not one now, but two carbon dioxides that will let go of the platinum. So we're going to propose this. And like I say, there are ways to test. We can never prove a mechanism. Remember, it's science. We can't prove anything. we can prove if a mechanism is wrong. But we can never prove if it's right. But here's a new mechanism we're going to propose. Notice that this platinum carbon monoxide cancels. Notice that this platinum carbon trioxide cancels. And notice that the platinum actually cancels as well. So our catalyst is involved in the reaction, but it's not in the reaction. It doesn't actually stay in the reaction, so it does not react. But now what's left? We have 2 carbon monoxides. We have 1 oxygen. Everything cancels but our 2 carbon dioxides here. If it does not add up to your overall reaction, it is not a valid mechanism. Like I said, we can disprove something. So that's the first test, just the first test. So now we have a new mechanism for how the reaction occurs. And this is how catalysts act. This is why heat is not a catalyst. Heat is an energy input. It's a source of energy. It's not a catalyst. A catalyst is never consumed in a reaction. So what's actually happening here? The catalyst is speeding up the reaction by providing an alternate pathway for the reaction to occur. That's what catalysts do. They don't change the reaction. They don't cause reactions that occur if they don't occur naturally. The only thing the catalyst can do is to provide an alternative pathway to the chemical reaction. So if the reaction doesn't occur naturally, you can add all the catalyst you want. It's not going to occur. It just doesn't work. But it speeds up a chemical reaction. And this is why, by the way, catalysts can never slow down chemical reactions. Catalysts can only speed up chemical reactions, because if it turns out that this pathway is slower, we still have the original pathway to go. So if the catalyst creates a pathway that's actually slower for the reaction to occur, why would the reaction use that pathway? It's going to go the faster way. So the original pathway is still there. It's still active. It's still happening. But now there's a new pathway. And if the pathway is faster, it speeds up the chemical reaction. So catalysts are not consumed in the reaction. They provide an alternative reaction pathway, but they can only increase reaction rates, never decrease. We can still use that old pathway if we want. So, hang on a sec. I noticed that Kim has disappeared from us. And yeah, okay. Kim is so kind. She does not have to be here if she doesn't want to be here. Hopefully she does want to be here. I hope that she is